So for our nice warm-up problem, we have the following. Consider f of x is negative log x squared minus 2x plus 2 arctangent of x minus 1. The linearization of this function at x equals 1 is L of x equals 2 times x minus 1. And this gives that f of 1.05 is approximately 0.10. So they gave us a lot of information. Using the second derivative, which of the following is true? So we have an estimate, but now the question is it a little bit bigger or a little bit smaller? So we have a couple of options. Depending upon whether the second derivative is positive or second derivative is negative, whether or not we think something is bigger or smaller. There might also, of course, be that the second derivative is 0, which doesn't tell us anything. Okay, good. Do we have an answer? Did someone find an answer?
A.
A, huh? Do we have another answer? Okay, now, are all of these potentially correct answers?
Yeah.
Let's think about this. So, linearization, what's another name for that? Tangent line. So, the clue is the word line. It's like, oh, linearization, that's a line. What's the line he keeps talking about in class? He keeps saying there's something line. Tangent line. Okay. So tangent line. So we have a tangent line. Here's our tangent line. We have our point of contact. Now, concavity tells us how we go off our tangent line. So if we're concave up, which side do we go on? Concave up is the upside. Okay, so if our second derivative were to be positive, our curve would look like this. So if our second derivative is positive, are we above or below our estimate?
Above.
So if our second derivative is positive, then we would have to be above our estimate. So B is out. Now, what happens if our second derivative is negative? We're concave down. Which side are we on? The downside. So that's our second derivative is negative side. So if our second derivative is negative, how do we relate to the tangent line? Now, tangent line is the guess. Are we above the guess or below the guess? We'd be below the guess if the second derivative were negative. So C is not a valid option. So just understanding concavity knocks out B and C. It's unlikely it's 0. So, knowing nothing else other than what concavity tells us in relationship to the tangent line, you should be able to narrow it down to two options, A or D. So you've got a 50-50 shot. Any guess?
D.
D. Because people probably said A. He didn't like that answer. It is D. Yes. All right, so what do? We basically just need to know what's happening with the second derivative. So we take two derivatives. So this is also testing us on logs and arctangents. And so this is a problem which probably is a little bit longer for a multiple choice problem, but it's testing us on some useful ideas. So the first derivative gets us to a polynomial over a polynomial. Use the quotient rule. And you can just plug straight in. You don't need to simplify. And when you plug in, you get that the second derivative is negative. It's the sign that tells us. So it's telling us that the function's below the tangent line, so the linear approximation is an overestimate.
What happened to the OS from the original?
So how do you take a derivative of a natural log? What's the procedure? Well, what's the derivative of natural log x? Do you remember the derivative of natural log x?
1/2
Yeah, so the derivative of natural log of x is 1 over x. The derivative of the natural log of f of x, if you use the quotient rule, here's how I do it. I write a fraction. The downstairs is f of x. What's the upstairs? The f prime of x. So that's chain rule. So it's 1 over, that's the coming from the derivative of log, 1 over the inside function times derivative of the inside function. So here the inside function is x squared minus 2x plus 2. That shows up there. And then the derivative of x squared minus 2x plus 2 is your 2x minus 2. So that's what happened to it. Any other questions? All right. Good. Well, on to today's thought. So, bit tongue-in-cheek. There are 24 hours in a day, and if that's not enough, then there are also the nights. All right. Now, if you actually try to search for this quote, I think you may end up finding me again online. Not because this comes from me, but because this comes from a friend of mine who I knew. And I wrote he passed away a few years ago. And I wrote some pieces about him. And he's one of these people who you look at and say, how is it possible that you've done all these things? You know, he was had multiple honorary doctorates, president of mathematical societies, 2 different mathematical societies, president of the International Drug Nurse Association. When he was a young person, he was a world-class trampolining artist. Just won all these awards. National Academy of Sciences, multiple National Academy of Sciences, not just in the US, but also in Hungary. And you look at it and say, how? How is it possible? And so this was one of his responses. And I asked him about this. I said, you know, I remember you telling me this. And he said, yeah, well, the one I really like is the following. There are 24 hours in a day, and that's true every day. And I think a lot of this sort of comes back to, like, how do you make the most of your time? And I don't want you to overload yourself, because there's such a thing called burnout. If you haven't experienced it yet, good. I hope you never do. But some people try to put too much on their plate. And it's negative. It's negative to your mental health. It's negative to your physical health. So being productive is not about cramming as much as you possibly can into your schedule. Being productive is about making the most of the time that you have. You have 24 hours every day. Make the most of it. And sometimes that might mean going to jump on a trampoline. Sometimes it might mean getting ready for your math exam. Just make the most of the time that you have. All right. That's the thought for the day. So, today, it's actually incredibly short, the theory, but the problems will take us a while. So we're talking about optimization. So optimization is a really important subject. It's one of the reasons that people still care about calculus. It's like, we're trying to make the most of what we have. And when you're faced with situations, you usually have trade-offs. You say, well, I could do more of column A, but that costs me a little bit in column B, and I lose something. But I might switch and say, okay, do more of column B, but again, I lose something from column A. So it's like finding the right balance between your options. And so that's optimization. So we're like, it's like maximizing and minimizing. Yes, it's exactly that. It's like, we've got tools. Yes, we have the tools. So what's new? Well, mostly it's we're adding words. So this is word problems, most of these. So how do we do these problems? Well, first off, we have to understand the problem. We can't find the optimal solution if we don't understand what's going on. So we have to think about, okay, what is it that we're trying to optimize? What can vary? Do we have multiple things that can vary? Now, in our class, we're pretty good with just one thing that being varied. And so sometimes you have to say, if you have multiple things that are in play, you have to say, how can you get it down to just a single variable? And so that comes from looking for relationships. And another thing that's closely related is drawing pictures. If needed, draw a picture. Sometimes they'll give us a picture. We're trying to understand. And then if you have a picture, throw in some labels. Get some intuition about what's going on. Ultimately, the goal here, this is step 2, is we want to say, once we understand, we want what we're trying to optimize to get down to a function of one variable, one function to rule them all. And then we say, we have the technology. We look for critical points. So we take the derivative. Where is it 0? Where is it undefined? Do we need to worry about endpoints? Sometimes yes, sometimes no. And so we go through and we figure out what's happening. And then we give our answer. Sometimes it might say, find the maximum volume. And then the answer is a volume. Sometimes it might say, find the dimensions that produces the maximum volume. And in that case, our answer is a set of dimensions. And so it really depends on what the question is asking as to what we put in. Now, sometimes, not all the time, but I just want to be sure we're ready for this. Sometimes we might need to justify why it's a max or min. Now, do we have tools that help us justify being a max or min? I see one person is nodding. Yes, okay, good. It's a yes/no question. That's the classification tools, right? It's like, how do you tell if something's a max or a min? Well, you can use first derivative test, or you can use second derivative test. And we stop there. There's no third derivative test. So use the test. All right. So that's the theory. The rest of it is practice. Are we ready for practice now? All right. Good. So here we go. First problem, warm-up problem. We're given 400 feet of fencing. And we're asked, what is the largest rectangular pen that can be formed against a cliff? All right, so let's draw our picture here. So what do we have? We have a cliff. So this is our cliff. So the nice thing about a cliff is it makes a natural boundary. And when we're thinking about a pen, we're trying to bound something. We're trying to have sort of this bounded region. Like, for example, we're trying to keep animals inside. So we need only 3 sides of the pen that have fencing. So we say, okay, so it's probably going to look something like this. So here's our pen. And how do we find the largest rectangular pen? What is the largest rectangular pen? Okay, so that's sort of the picture. That's our situation. Does it make sense, the question? And you might say, well, does it matter? Well, we could do silly things, such as make a pen like that. That's probably not efficient, though.
Triangle?
Well, rectangular pen. So it's hard to make a rectangular pen a triangle. I mean, you could, but you'd be Yeah, it's hard to make. It turns out circles are really the best, but okay. So, yes?
We have more than one?
Can you have more than what? One pen? What is the largest one rectangular pen? Just to be clear, there's only one pen. We're using all the fencing on one pen. And it's a rectangle. It's not a pentagon. It's not an octagon. There's no MMA here. It's just rectangle. All right. Cool. How are we doing? Now do we understand the problem? Okay. So, we should label stuff. What would be some useful things to label?
The 3 sides.
Okay, we should probably label the 3 sides. So, let's label this side. How long is this side? W. How long is this side? H. How long is this side? W again. Ha ha ha. We're going to take advantage of the fact that it's a rectangle. Okay. Now, what is it we're trying to maximize, make as large as possible? Area. They might say, wait, it doesn't say the word area. So we'll add it in. Just since apparently I'm getting in trouble when I don't put in all the words. Okay, so we're trying to maximize this quantity W times H. But we can't choose W and H arbitrarily. You know, like I can't be like, oh, make W 1,000 feet long, or because what's a restriction? We only have 400 feet. So what does that tell us?
It can be 200 feet. 2WH.
So if we add up these 3 sides, that has to be 400. So 2W plus H has to be 400. Now you might say, well, could I use less? You could, but you'd get something smaller. So we really are after using every piece of fencing available. Now, our goal is to get down to one variable. How do we do this?
Solve the given for the variable.
Okay, so we can take our relationship and solve for one of the variables. Good. Does it matter which one we solve for? No. But we're going to solve for H. Why are we going to solve for H? Because I'm a tyrant. No, that's not why. If you solve for W, what do you end up getting? You end up getting fractions. I'm someone who is nervous around fractions. I've lost so many points in my life to fractions, I try to avoid it. So I would prefer to solve for H, but I understand your generation is a different generation. And you might have a different feeling about fractions than I do. We could solve for W if you want. We'll solve for H here. You will get the same answer either way. Okay, so H is 400 minus 2W. So then we could say, we're trying to maximize W times 400 minus 2W. So let's give this a name of a function. The area of W is W times 400 minus 2W. Or, if you like, 400W minus 2W squared. Okay, now what? We've gone down to a function of a single variable of what it is we're trying to optimize. This is good. So now we're ready to pull out our wonderful calculus tools. So what do? Take a derivative. What's the derivative? (400 minus 4W). Okay, what do we do with this derivative? Yeah, we're looking for critical points. It's never undefined. Now, there are some boundary points, but let's sort of avoid that discussion for a second. So 400 minus 4w is 0. What does that tell us about w?
W equals 100.
W equals 100. All right. So w is 100. What would h be? So it's 400 minus 2 times 100, which is 200. So the claim is that the largest we can do is 100 feet by 200 feet. So that's the largest rectangular area. It would give us a total of 20,000 feet squared of area if we wanted it. Are we sure that's the maximum area? Now, because when you're doing optimization, you're finding critical points. Not every critical point is a max. Some are mins. How can we be sure it's a max? We can just sort of reason that we have these extreme cases. So, for example, if I put 200 feet of fencing here and 0 feet of fencing here, that's a valid fence. How much area is there? 0. I could also put 400 feet along the cliff with nothing coming off the cliff. That's also a valid fence, which is 0. So that's sort of the extreme cases. So I could argue by the extreme cases. But what if we wanted to use calculus tools? Okay, first derivative test or second derivative test? Which one do you want to try? First? Yes, I see a hand up.
Can you also just reason that since it's a second degree with a negative, then it's just going to be, it's going to have one maximum?
Oh, you can do a lot of reasoning, yes. Usually you can just reason like, I'm asked to find a max, I found one, it must be the max. It's unfortunate that it's the kind of points that they don't give you, it's the kind of response where they don't give you the full points. And we want all the points. So you can do a first derivative test, and you can say, okay, pick something on either side of 100. What's something below 100? 50 or 0. Plug it into your derivative. What do you see? Is it positive or negative? It's positive. Pick something bigger than 100. 101. Plug it into your derivative. Positive or negative?
Negative.
Negative. So then by first derivative test, this is a max. How would the second derivative tests look, by the way? You take the second derivative. What would the second derivative be?
-4.
A double prime is -4. You mentioned, oh, can't you reason since you have negative something squared? It's also coming back to the second derivative test. Your second derivative is negative. That says, this is a local max by second derivative test. But since it's a local max and there's no other maxes, it's a global max. All right, cool. Well, that took us a while. So let's skip that one. Any questions on this one? So here's one. So your analysis of past parties has led to the creation of a chip index, n squared p, where n is the number of bags of nacho chips and p is the number of bags of potato chips. Given you have a budget of $18 for chips, nacho chips cost $3 per bag, potato chips cost $1 per bag, then how many of each type of bag should you buy to have the most awesome party? And the implication is the higher your chip index, the more awesome the party. So just to clarify how I'm measuring awesomeness. Yes?
Why would we just only bought potato chips?
Well, then you would have a bad party, because what would your chip index be? If n was 0, that's just not a good blend of chips. So you don't just want potato chips. That gives you a 0 for your chip index. So you then say, oh, just buy nacho chips, right? But then, if you just buy nacho chips, what happens?
You get a 75.
Well, you end up with no potato chips, and your chip index goes to 0.
Well, that's why you buy the most amount of nachos without at least taking a potato chip, and then it's just 25 times 3, which is 75.
Well, but now we might have to be careful, because nachos are expensive.
Yes, you only get 5 nacho bags, sure, but you get 3 potato chips.
Ah, is it best to buy 5 bags of nachos? So here's the question. What's the optimal blend of nacho chips and potato chips? Do we have the right blend of nachos and potato chips? Somebody suggested 5 nachos, 3 potato chips. Can we do better? Can we have a better party? 4 nachos. Yes. Okay. So, we know what we're trying to optimize. We have our budget to work with. So that tells us that 18 equals 3n plus p. We can replace p in terms of n, get down to a single variable, take a derivative, set it to 0. Obviously, no nachos is a bad party. And so 4 nachos, that's a good party. Gets a 96 on our chip index. And so that's the right blend. And you can use a second derivative test or a first derivative test to show it is indeed a max. All right, cool. Well, let's try another one. Find the points on the curve y equals x squared nearest to the point 0, comma a. Now, we aren't saying what a is, so a can change. So you have this y equals x squared. It's a parabola. And we have a point 0, comma a. So here's 0, comma a. So, all right. What is it we're trying to optimize? Like, what's the key word for us? Nearest. Now, it's usually pretty easy to identify. The key thing is you look for the est and say, okay, whatever the est is in a problem, that's what you're trying to optimize. So, okay, so we see nearest. So we have this sort of, we're trying to optimize being near. Well, being near is a measurement of distance. So this problem is trying to optimize the distance. So we say, all right, well, let's think about what's going on. So we have our point 0, comma a. What does a typical point on a parabola look like? Can we write it in, say, one variable? Because we can write any point as x, comma y, but what do points in the parabola look like? They look like x squared. That's our point. All right. Well, what's the distance? How do you find the distance between the point x, comma x squared and 0, comma a? Now, keep in mind, while we don't know what a is, treat it like a number. So what's our distance? Is there a formula for distance? Yes, okay, there's a formula for distance. What does it involve? Distance is the square root of, you take your x minus 0 squared. So look at your x coordinate entries. Take their difference squared. X squared minus a quantity squared. So this looks like the function we want to optimize. But I can't help but notice that there's something unappealing about this function. Sorry, what? What would we not want to have to work with? Square root. So we're not going to work with the square root. So let's not optimize this function. Let's optimize this function, d squared. Now, question for you. If I make this as small as possible, will I also make this as small as possible? So in other words, if I'm minimizing the square of the distance, will I also minimize distance? Yes. Because if you're trying to make distance as small as possible, the way you do it is make what's inside the square root as small as possible. Now, are we down to one variable? Well, yes, there's just x's. A is like a number. Now, I'm going to square this. So that's x quantity squared. This will be x to the fourth minus 2a x squared plus a squared. Okay, so we've gone down to a single variable. We'll call this f of x for lack of a better name. What would be the next step? Yeah, take a derivative. The good old take a derivative trick. Okay, so what's the derivative of this function? Derivative of x squared, 2x. Derivative of x to the fourth, 4x cubed. Derivative of 2ax squared, 4ax. Derivative of a squared, 0, because a is acting like a number. So a squared is a number. Now, we can do a couple things. We can combine the x terms together. We could have done that in the previous step. So that's really 4x cubed minus 4a minus 2x. Now what do we do? Okay, find critical points. So what do we need to do? Set this equal to 0. Oh, this is going to be fun. We've got a cubic. Ha ha ha. Ha ha ha. Ho ho ho. Okay. So, anything we can do to help solve this? We've got 4x cubed in the first slot. We have this minus 4a minus 2 times x in the second. Do they have anything in common? They have an x in common. So if they have an x in common, what should we do? Let's factor an x out. So x times 4x squared minus 4a minus 2. Okay, so that leads us to two possibilities. So first question, when does x equal 0? Well, the answer is when x equals 0. The second, when does 4x squared minus this quantity 4a minus 2 equal 0? Well, okay, move the 4a minus 2 to the other side. 4x squared equals 4a minus 2. X squared, divide both sides by 4, would be a minus 1/2. What would x be? Plus or minus the square root of a minus 1/2. And we're okay with plus or minus because there's this symmetry. If we have a close point to the left, the flip it on the mirror, there's the same close point just across. Okay. Well, something weird is going on here. Because we have 2 points. So which one's the right answer?
They all
They all are. That's a bold answer.
Well, you have the 0, so that's whatever A is distance away, right? And then you would just have, eventually you'd have that same distance again, right? If you go along the curve.
Would we? Well, you said that they're all right. Well, that's kind of half true. They are all right, but they're not all right at the same time. Let's start with 0. Let's take a look at the second derivative. Because we have the first derivative. The second derivative would be 12x squared minus 4a minus 2. So let's talk about the second derivative at 0. That would be, well, minus 4a minus 2. Now, there's a couple of cases. Now, when it comes to the derivative and the second derivative, what do we care about? Well, it tells us concavity, but wait, what? The sign! We saw the sign, and it opened up our eyes when we saw the sign. Okay, so there's a couple of cases. What happens if a is equal to a half? What's the sign of the second derivative? It's 0, because 4 times a minus 2 is 0. What if a is bigger than a half? It's negative. Now, if the second derivative is negative, what does that tell us? It's a frowny face, right? If it's a frowny face, that means we are a max. So 0 is not close, 0 is far. Now, it's not absolutely as far away as you can be. It's a local max. What happens if a is less than a half? You end up with something greater than 0. So what does that tell us? It tells us we're at a min. So 0, and by the way, just so we all agree, 0 is this point here. 0 is a good point for some values of a, but not for others. So when is 0 a nearest? In other words, when is it a min? A is less than a half. Now notice, come over here, what happens when a is less than a half? What's happening? It becomes negative inside your square root, which is rather complex. Sorry, some math humor. Okay, so we don't like negatives inside our square roots. So what's the unraveling here? So what's the punchline? Because there is a punchline here. So if a is less than or equal to a half, so in other words, a is kind of small, then the nearest point is at the origin. What happens if A is greater than a half? So if A is greater than a half, it's not the origin, so where is it? It's the other points that we found. So where are those? They're at plus or minus square root of A minus a half, and that's the x, and then the x squared is A minus a half. So there's sort of this transition point depending upon your choice of A. Now there is a punchline here. Okay, so what's the punchline? And because we're basically out of time, but I do want to mention that this tells us something about this parabola y equals x squared. If you have this parabola y equals x squared, and you put a circle inside of it, one of two things will happen. Either you'll try to put the circle in and it'll touch the sides, or you'll try to you'll touch the circle, and where will it go? It'll rest at the bottom. Now the question is, where's that sweet spot? If the circle has radius, if the radius is less than or equal to a half, it sits on the bottom. If the radius is greater than a half, it won't reach the bottom. That follows from this computation. I'm not saying it's immediate, but it does follow from the computation. All right, we will do more practice next time.